Hello, nephrons. Today we will be talking about acid-base problems. To start off with, we'll discuss this graph. On my y-axis, I have carbon dioxide here, and on my x-axis, I have the pH. For all practical purpose, we were going to be assuming 7.4 as the normal pH, 40 as the normal. And as you can see, if a guy has about 40 and pH 7.4, he is assumed to be normal. Let's assume a scenario where somebody is having pH and PCO2 right around here. I'll give you a few seconds to think about this. You have to what do you think this guy is doing? Okay, as you guys guessed, when you look at this guy's pH is low, which means that he is acidotic, and this guy's PCO2 is also low, which means probably he has a metabolic acidosis, and this guy is trying to compensate by blowing out his PCO2. Now let's assume a scenario here is, of course, it looks the same, but just a little bit of variation in pH as well as the PCO2. How about a guy around here? Okay, as you guys guessed, this guy has an alkaline pH and this guy's PCO2 is high, which means probably this guy has a metabolic alkalosis and he's trying to compensate by retaining more PCO2. So if you imagine this scenario, you will know that anybody in this line is trying to be, it's not an accurate line, but you get the gist of it. Okay, anybody along this line will be doing a metabolic process. Now when I talk about a metabolic process, what you have to understand is the kidneys are a less efficient system than the lungs. What I mean by that is whatever the lung does, the kidney cannot catch up instantly. But when you look at the vice versa situation, whatever the kidney does, the lung can catch up very quickly. And that's why you only have one kind of metabolic process and you have two types of respiratory process, because whenever the lung makes a change, the kidney needs more time to catch up. Now let's look at another scenario. What is a guy right here? What is he doing? Okay, you guessed it right, that this guy's pH is low while his PCO2 is high, which means that he is having respiratory acidosis, that he is retaining PCO2 and that's causing him to be acidotic. How about a guy right around here? What is that guy doing? Yes, you guessed it right. That guy has a respiratory alkalosis, that his pH is high and he is blowing out his PCO2, low PCO2. So just like I mentioned earlier, anything along this line, you know that that guy is doing a respiratory process. Now if I draw a line parallel to that right around here, which one of these red lines will be an acute process while which one will be a chronic process? Okay, so in order to come up with that answer, you look at that PCO2 and you compare, like right around here one guy is there, and right around here you have the second guy. Both these people have the same PCO2, but you know that this guy has a far lesser change in pH compared to this guy, which means this guy had time to compensate. This guy's kidney caught up a little bit, so that makes this guy the chronic guy and this guy the acute guy. And this is the metabolic guy and this is the respiratory guy. Okay, now comes to the main part. It's the compensations. All the compensations I will be representing that as um, bicarb over PCO2. So let's start with the metabolic acidosis. In metabolic acidosis, we'll start with a bicarb change. For every bicarb change by 1, the PCO2 changes by 1. What this means is that, let's say, metabolic acidosis. So let's say the bicarb went down from 24 to 23. The PCO2 will change from 40 to 41 to compensate. Like I said, lungs are much efficient system and they catch up very quickly. Let's talk about a metabolic alkalosis. For every 1 change in bicarb or every 2 change in bicarb, the PCO2 changes by 1. Same scenario. Let's go to the respiratory processes. Let's start with the acute respiratory process, which means the kidney doesn't have enough, hasn't done anything to catch up at all. So that's because it's a respiratory. We'll start with the PCO2. For every 10 change in PCO2, for every 10 change in PCO2, the poor kidney can only catch up by 1. And for a respiratory alkalosis part, for every 5 change in PCO2, the kidney catches up by 1 only. And when it's chronic, as I said, the kidney has more time to catch up, and this guy, for every 3 change, he caught up by 1 already, and over here, for every 2 change, he got up by 1 already. So this graph, you just have to remember this graph. There is no easy way around. As I mentioned earlier, if you are a visual person, this might be easier for you. But if not, just keep drawing this, and if you can remember this graph, this is an easy way to approach compensation rather than going through all those complicated equations, log this and log that. Let's get to the next slide. This graph, almost a simplified version of these complicated graph that we see in all those textbooks. But as I mentioned, that graph is all. Now, coming to the main part, the 4 steps involved in coming up with the answer to an equation. I'm gonna start with a metabolic acidotic process because that's the easier way to come up with the answer, and that's the most common scenario that you'll be faced with on day-to-day life. So first step involves getting the anion gap. By now you might know how to calculate the anion gap. Second step involves calculating the delta gap, which is anion gap minus 12. Some people use 10, some people use 12. I'm gonna be using 12 in this video. The anion gap, of course, if you have an albumin problem, you correct for the albumin. That's up to you guys. Third step involves adding the product, that is the delta gap from this, onto the bicarb. When you add the delta gap onto the bicarb, you're gonna come up with some number. What you do is you're gonna compare that to the normal bicarbonate level, that is 24. If this added product of these two is more than 24, then you have a metabolic alkalosis along with whatever you have here, whether it's an N-gap acidosis or not. Second one is if this when the added product of these two is less than 24, you have an additional metabolic acidotic process. This might sound confusing right now, but when we go through one problem, this will become clear. And the fourth step, of course, involves using the graph to come up with the compensation and seeing if it's adequate or more. Once we solve one question, this will become much more easier for you guys to remember. pH is 7.2, PCO2 is 30, and then bicarb is 10. You know by this that this guy is having a metabolic acidosis because the bicarb is low, and the pH is 7.2 and PCO2 is 30. So the first step involves calculating the anion gap. The anion gap is 140 sodium minus the chloride plus the bicarb. Nice rounded numbers. You have 20 is the anion gap. Step 2 involves calculating the delta gap. Delta gap includes the anion gap, that is 20 minus 12. I'm going to be using 12. You can use 10 if you wish. So that gives you a number 8. Now step 3, as I mentioned, involves adding the delta gap onto the patient's bicarb. So that is adding this 8 delta gap plus 10, which brings him only up to 18. As I said, 18 is less than 24, which is the number the normal bicarb we compared to, which means he has an additional acidotic process. Because he has anion gap here, we know he has anion gap, metabolic acidosis. And by now, because he hasn't, he's still deficient in bicarb, we know there is an additional acidotic process. This is the non-anion gap metabolic acidosis. Assume, for example, if this number was, let's say, 28, which is more than 24, then he has an additional metabolic alkalosis because it's more than 24. And if it's right around 24, you know that there is no other processes, there is only the anion gap metabolic acidosis to start with. And step 4 involves looking at the graph for the comparison. So we know it's a metabolic process, so we're gonna go back to and use the graph to look at a metabolic process compensation. So because it's a metabolic process, we're gonna be using 1/1, like for every one change in bicarb there is one change in PCO2. This is what we expect in metabolic acidosis. So let's look at the change in bicarb. A change in bicarb right around here is around 24 to 10. So he changed about 14. So a normal person, when he has this much of change, we expect his PCO2 to change by 14, 1:1. So from 40 he should have come down to 26. Right? Now let's look at what this guy is doing. This guy is actually doing 30. So this guy is actually having more PCO2 in his body than what is needed. When you have more PCO2, you know that that guy also has an additional respiratory acidosis. That's it. That's all you need to do. Need to come up with all the 3 answers. Down the video I have provided some more sample questions. You can refer the website for more equations, and probably in the coming days I might do one more video solving a couple more questions which would make it easier. So if you like this, have any questions, please comment below, subscribe and like if you like that, and I'll keep adding more and more videos in the future. Thank you guys. We'll see you with the next video. Take care.